Hello. Let me just start off by saying I started my life as a ground-based observer. I never thought I'd be involved in a planetary space mission, but when you hang around planetary astronomers, you get kind of pulled into that. So I've been lucky enough to be on several planetary missions, Rosetta and New Horizons, but I'm going to tell you about Lucy, an upcoming mission to the Trojan Asteroids. And I just want to give thanks to Hal Levison, who is the PI of the mission. He's also at Southwest Research, and Kathy Olkin for most of this presentation's content. Like I said, when I was a ground-based observer, I was studying massive stars in the Magellanic Clouds, OB associations. So even though I've been doing planetary now for 25 years, I still feel new to the field because it's not what I did in grad school and postdoc. So first of all, just to give you an outline of why it's even called Lucy to begin with. So this is a NASA mission to go to a never explored before group of asteroids. We call them, and I'll justify this later, fossils for planetary formation. And so the name Lucy, one of the connotations is to the Lucy fossil that was discovered that told us about our human origins. In the same way, in the usual public relations pitch that you do to NASA, this will tell us about our origins in the solar system and the origins of the planets. So where will Lucy be going? The Trojan asteroids are at the Lagrange points of Jupiter's orbit. So the L4, which leads Jupiter orbit, and L5, which trails Jupiter. These have never been explored by a spacecraft before, and they're nice, stable orbits. These orbits have a stability effectively the age of the solar system, or the age of the formation and stability of Jupiter's orbit. So things that have been captured in those orbits have been there for a very long time. So we think these are really the not very disturbed remnants of the early formation of the solar system. And so that's why we're interested in going there and exploring them. Lucy is going to do, not visit one, but is going to do a tour of the Trojan asteroids. So it launched already. It launched almost 2 years ago in 2021. It will have a flyby of 2 main belt asteroids and then 8 Trojan asteroids. Now, we started with 6 Trojans, but then we discovered a moon, so then it was 7 Trojans, and then we discovered another moon, so technically we now have 8 Trojans, total of 10 asteroids in a 12-year mission. This is the most asteroids any mission, single mission, has visited. So why do I say that these Trojan asteroids are fossils of the formation of the solar system? And this goes to the models of solar system formation that are currently in good stead. One is called the Nice model that some colleagues developed while they were in Nice. But the idea is to boldly go where no one has gone before to visit these Trojans. They have a very diverse range of colors, diverse range of reflectances or albedos. And so we believe that those colors are indicative of formation history because they were all, since they were captured, they've all been in the same environment. So the colors are probably not due to environmental effects, but due to origin effects. And this is a little cartoon of the idea behind the Nice model. So we have the sun and then the 4 planets. If you talk to my dynamicist friends, they say our solar system has only 4 planets. So we have Jupiter, Saturn, and then the 2 outer ice. Let me see if I have the cursor here as well. Yes. So note the dark blue one is closer in, and the lighter blue one is further out. Also note, this is the debris disk that the solar system formed out of, and these have been color-coded gray, yellow, and orange from roughly 15 AU to 30 AU, where an AU astronomical unit is the distance from the sun to the Earth as a yardstick. So we're going to start this animation now, and the idea, keep your eye on the ball. We have a scattering event of one of them off Saturn. It scatters out into the disk. As it goes out into the disk, it scatters many of the particles away. Several are captured in these Trojan orbits of Jupiter. And note that through the whole range of the disk, as that planet went out, it scattered many outward and many inward. Some of the inward get captured in the Trojan orbits. So basically, by this scattering event, we get samples throughout the disk coming in and captured in the Trojan orbits. So visiting just the Trojans gives us a unique opportunity to actually sample different distances from the sun during planetary formation. So let me blink back and forth for a minute here. Here's where I started, and here's the end state. So note, Jupiter moved in a little bit from its original formation location. Saturn went out, and the planet we call Neptune, the one furthest out, if you look back, that's the one that actually was closer in. It actually swapped spots with what we call Uranus. So the solar system formed in a much more, in this model, much more compact form of these 4 main planets and then a bunch of debris. And as far as the dynamic modelers are concerned, Earth, Venus, that's just more debris. Here's another model of the same thing, but looking down on a plane of the solar system. So again, look at the ordering of the orbits here. And again, we have the outer 4 planets. And note the dark blue is the second to the last orbit there. Now, this is a somewhat old model here. Around 880 mega years, you'll see a change. But now we think it happened much sooner. But you can see there's little bits of scattering, things going on. The orbits are relatively stable. And then the blue orbit will have a chaotic event. And within a very, very short time, it goes out, scatters into the disk, scatters most of the disk away, some things in. Even the things that go in, if they hit Jupiter, they get captured or they get scattered out. And that leaves us with the solar system we know. So here's the solar system. Again, the 4 main planets, and then we put these in to make our terrestrial researchers happy. But these are the stable objects in the solar system, in dynamically stable orbits. So we have the planets, we have the asteroid belt with the gaps in it, the Kirkwood resonance gaps, which are resonances with Jupiter. We have the Trojans. By the way, so this is distance from the sun, and this is the eccentricity of the orbit. So don't have much. We have a few Neptunian Trojans, but then we have the Kuiper belt. So everything beyond Neptune, we have the cold Kuiper belt, which never got scattered. We have excited Kuiper belt and some that are in resonance, such as Pluto, which is in a 2 to 3 resonance with Neptune. And then this tail here, which is the scattered disk. All of those objects that got scattered out into a disk or some actually got scattered even further out. So these reservoirs were created during the formation of the solar system. The resonances you see in the Kuiper Belt were captured resonances as Neptune moved out. It was able to capture and push out objects that were in those resonances. So these really are, the remnants of planet formation during this early few 100 million years formation period of the solar system. And all of these reservoirs have been studied by spacecraft except the Trojans. Even though spacecraft have not gone out into the scattered disk, these dashed lines indicate where objects were, such as the Rosetta mission, observed a comet. That comet, although it was a Jupiter family comet, it originated out in the Kuiper Belt in the scattered disk. So we have had missions to every resonant and every small body population except the Trojans. So it is the last unexplored class, which we will solve that with the Lucy mission. So let me give you a little outline of what the targets are that Lucy is going to observe. In the L4 swarm, so this is the Lagrange point leading Jupiter in its orbit. In the L4 swarm, we have Eurybates and its moon Keta, Polymele and its moon, which is currently nicknamed Sean. It doesn't have an official name yet. Both these moons were discovered, this moon was discovered just before launch. This moon was discovered after launch. Then Lucas, Orus, that completes the L4. And then in the L5, we will visit the Patroclus Menelaus binary. This is actually a binary system. So we will be visiting 8 Trojans in both swarms. 3 of them are multi-body systems. So the moon, Keta, was discovered with the Hubble Space Telescope. If you look very carefully, there's a little green circle just up there. That is, the little dot in the middle there is the detection of Keta. The Sean satellite of Polymele was actually discovered during occultation runs. Ground-based occultations can do an amazing job of determining shapes, looking for atmospheres of otherwise unresolvable objects in the solar system. So we have especially with the Gaia catalog now, we have exquisite positions of stars, good ephemerides for the positions of these targets. So we know where the star shadow is going to pass the Earth. So we have these small telescopes that we take all over the world to stand in the shadow of a star as a small asteroid passes in front of it. And the surprise with Polymele, we were just interested in getting Polymele. But the observers, so what you see here is basically we fixed the positions of the asteroid, and these are basically the star trail. We keep the asteroid fixed. This is the star trail going behind. When the star blinks off and then blink on, we have one chord across the body. Many chords give such a shape of the body. And we got a little teeny blip, unexpected afterwards. That was the discovery of this satellite of Polymele. Eurybates is interesting because it is a member of a collisional family. Basically, another asteroid hit a parent body, it disintegrated. All of the bits and pieces left orbiting have dynamic orbital relationships, and they're a family. So what I will show here is a little animation of the disruption of this, and you'll see the formation of satellites around the remaining largest mass parent body. So that is likely how Eurybates and its moon Keta were formed. And then we have just the large double binary of Polymele and Menelaus. And this is a Hubble Space Telescope image of those two bodies. One key factor, other than we're going to get to see a lot of them, is we're going to sample a lot of colors and reflectances, or albedos, of objects. So this plot on your left shows the range of albedos, reflectances at different wavelengths. This is a WISE albedo, and this is a visible albedo. And you can see that the colored dots, we cover a good range, a good coverage of the range of the albedos. Similarly for the colors, this is a color plot, and our targets also cover a good range of colors there as well. We also cover a good range of sizes. This is a very nice graphic done by Emily Lakdawala and the Planetary Society of all of the small bodies observed, visited by a spacecraft. Two are not shown, Ceres and Vesta, because they are very large. This one here is 132 kilometers across. Ceres and Vesta are over 900 and almost 600 comparatively, so they'd be extending well past the room. But just to give you an example of the range that we're covering in sizes, Dinkinesh, which is one of the asteroids I haven't talked about yet, and Keta, that moon, are on the order of 1 kilometer in size. So that's the size of these smallest asteroids like Ryugu, Bennu, which have been recently visited, Dactyl, Didymos, and Braille. Donald Johanson, which is another one of the main belt asteroids, and Sean, the moon, are on the order of 4 to 5 kilometers. So that's Steins, Tutatis, and Anfrank, as well as Wild 2 and Churyumov-Gerasimenko, which was the target of the Rosetta mission. Polymele is roughly the size of the y-axis of Comet Halley, and the main body of Arrokoth. Arrokoth was the Kuiper Belt object that the New Horizons missions visited after Pluto, another billion miles past Pluto. Interestingly, Polymele is not only similar in size to the body of Arrokoth, but in shape. Both of them look like flattened hamburgers. We learned this from Arrokoth by flying by. We learned it from Polymele from the occultation observations. Forming a hamburger through different modes really can limit the models that you have for planetary accretion and formation. So just knowing a shape can tell you a lot about how things formed in the solar system. Lucas is now roughly the size of the whole Arrokoth, as well as some of these medium to larger sized asteroids, such as Ida and Eros. Euripides and Orus, similar there to Matilda. And then the big binary, Patroclus and Menelaus, close to the size of Lutetia. So all together, the Lucy mission is going to sample a size range that spans the sample of all the objects already visited by all other spacecraft for small bodies. This is just another way to look at the results here. We have size the H magnitude or the size, and the color, red going upward. So you can see that in this space of size color space, we cover it well, but even among themselves, we have good cross comparisons. So for example, we have two objects that are similar in size but very different in color, but on similar orbits. We have two objects that conversely have very different sizes but similar colors. We have three objects that are likely have different formation histories, primordial versus collisional fragmentation forming. And then we have a very slow rotator, Lucas, which has a 446-hour rotation period, extremely slow. So this large number will allow us to not only compare to asteroids in the main belt, but even cross-compare within the mission itself, similar and different characteristics. So here's this image again of where the location of Lagrange points are, and then this shows where the Lucy targets are that we'll be going to. These in the L4, this one in the L5, Donald Johanson in the asteroid belt, and then Dinkinesh, which I'll talk about in a minute, is also in the asteroid belt. So this is the tour. And it's, again, the PI of the mission is a dynamicist. This tour is a dynamicist's dream because of how well it works and how stable it is and how you're able to visit the asteroids in all the swarms. So as I mentioned, we had launch in October, and we set off from Earth for the first year, a simple one-year orbit to get our next Earth flyby. So we had this Earth swing by that happened last year. That bumped us out into a slightly larger orbit. And right about now, we're passing by Dinkinesh on November 1st. So let me just mention, Dinkinesh was not part of the original mission plan and not even part of the plan after we launched. It just so happens one of the members of the science team was looking at the orbits of basically all the asteroids in the asteroid belt and noticed that we were going to already, just our normal trajectory, fly very close to an asteroid. And if we just did a little nudge, a very slight sidestep, we would be able to do an encounter of another asteroid. And this was perfect for a number of reasons. It gave us an early rehearsal of the automatic, autonomous tracking that we're going to use when we get to the Trojan asteroids. And also just as a team, work together and practice doing an encounter. Otherwise, we would just be sitting around twiddling our thumbs and bored, right? So we're getting ready for this encounter to happen very soon. In fact, we've already started taking navigation images. So we have then after that, our next gravity assist from the Earth, which then will take us very shortly to Donald Johanson. Donald Johanson is the person who discovered the Lucy fossil. Now, this may seem like an incredible coincidence that the Lucy mission will go by asteroid Donald Johanson. Luckily, that asteroid did not have a name when we planned the mission. So we were able to name it Donald Johanson, which, let me tell you, made Donald Johanson himself very happy. So he came to one of our science team meetings. He loved hearing about the mission. He was so excited. We loved hearing about finding Lucy. We were so excited. It's kind of like this mutual admiration among scientists in different fields. After the flyby of Donald Johanson, we now get to the L4 swarm. And this is a series of 4 encounters in a very short 15-month period of time operationally on a mission, that's crazy talk, but we're going to do it anyway. So our first encounter is with Euripides and its moon Keta. We named the moon, all of the Trojan asteroids were named after, Trojan War characters, but now, no, Keta was not in the Trojan War, but we're also naming after people from the Olympics. So Keta was a torchbearer for the Olympics, as well as a participant. So after Euripides, then comes Polymele, and then very shortly after that, our encounter with Lucas, and then finally after that is our encounter with Orus, which is the last Trojan in the L4 swarm. So now we've collected a lot of data and we're going crazy. All of this happens in 2027, 2028. These are very long missions. This is a 12-year mission. So of course, all of us do the math when we join these missions. Not only am I going to be, still working on the mission, I'm going to be still alive. The thing about a lot of these missions is they are intergenerational. And I really enjoy that. You get a new generation of scientists and engineers to train and take over a mission that you may not even be able to see to completion. So after that, we drop back in. We have another Earth swing by that we use to nudge our target point for the last object, which is that large binary in the L5 cloud, the Patroclus and Menenius. And that, in 2033, is the formal end of the mission. And after that, we send more data to the ground. In theory, we're done, but we could always, perhaps, propellant willing and resources, such as money willing, the mission could be extended. The great thing about this orbit is stable for millions of years, and it will continue to pass through the L4 and the L5 clouds. So in theory, we have job security. The Earth flybys are interesting in and of themselves. This is a graphic they made for the Earth flyby we had a year ago. We come screaming in very close to the Earth, 350 kilometers from the Earth. So that is below, not just low Earth orbit, but the space station, the Hubble telescope. So we came in at a speed of 15 kilometers a second, very low altitude. We had to track more than 47,000 satellites in Earth orbit to make sure we weren't going to hit any of them. Nobody would be happy with that. So we had collision avoidance planning all set out. Starlink, a lot of conversations with Starlink, but we made it through nice and clear. It wasn't like Star Wars through the asteroids, right? And we got good, interesting, useful data for that as well. First of all, this was a very nice PR bit. As we were coming into the Earth flyby, there was a lunar eclipse. So we were able to take these images of the moon go into eclipse. That was very fun. Maybe not data you would otherwise use, but scientists, we like to do fun stuff too. We also, with our terminal tracking camera, got this very nice portrait of the Earth and the moon. Here it is enlarged. And all of this, of course, is just ways of confirming that, yes, our instruments are working, they're up to spec, everything's behaving well. This is a nice couple pictures of the moon. Very good for crater counting, because we want to be sure that we can count craters on the Trojan asteroids, because craters are an indication of age. And the size distribution of the craters tells us about the size distribution of small bodies that have hit those objects. So being able to resolve craters down to a certain size is important, since we know the size of craters on the moon down to crazy small sizes. We could use these data as calibrations to test our cameras and our crater counting methods and everything to make sure things are working as expected. And also, just because people put things like these on spacecraft, we have a plaque on the spacecraft. It shows the orbit of the spacecraft and the planets when, I believe, when we were launched in a logarithmic scale. And then it has quotes from musicians and poets. Lucy, of course, one of the other connotations of Lucy is Lucy in the Sky with Diamonds with the Beatles. And the connection isn't that far apart, because apparently the Lucy fossil, when it was discovered, they didn't have a name for it yet. And that night they were sitting in a tent with their postdocs, and they said, well, we have to call it something. And suppose Donald Johnson said that this was the case. He said, Lucy in the Sky with Diamonds was playing on the radio when they were discussing this. Someone said, hey, let's just call it Lucy. So the name stuck. So there are quotes from all the Beatles on this, plus Yoko Ono. Yoko let us use a quote from John Lennon as long as we included a quote from her. And of course, Carl Sagan and others. And the one official astronomer rock musician, Brian May, also got quoted on this. So this plaque, though, is not a plaque to talk to aliens in the sense that we usually think of it, because this orbit isn't going anywhere. This orbit is staying home, basically in our backyard. So it's not so much a plaque to contact aliens in another solar system, but aliens of us in the future. Someday, however, centuries, decades, however long from now, they decide, let's collect all the spacecraft out there and put them in a museum. This will be our message to, our offspring. So here's the Lucy spacecraft. More than 500 people worked on the Lucy spacecraft. It was built over 14 months during COVID, and it stayed on schedule and under budget during COVID. So that in itself is a miracle. The people just did an exceptionally good job. I have so much respect for the engineers who built and tested the spacecraft and all the instruments. I want to mention this up here is called the instrument pointing platform. This is where all the instruments, all the cameras are mounted. Everything else is fuel, spacecraft, communication systems. So how big is it? So here's Lucy again. The width of one of these solar panels is almost about 24 feet, about 7.3 meters across. If you don't have quite a feel for that size and you are of a certain type of interest, maybe this comparison will make more sense to you. And actually, before I saw the spacecraft, I saw this, I went, oh yeah, okay, I know how big that is. So here is the instrument pointing platform with all the instruments mounted on it. So the Ralph instrument, the L apostrophe just means Lucy Ralph. It's not the palatalized L in Slovakian, but we have Ralph that flies on other spacecraft and Tess that flies on other spacecraft. So the L just means the Lucy version. It has an imager with multiple filters, and it's not movable filters, but we scan across. We have a scanning mirror, so we can point the spacecraft and then scan the mirror, and it will take the target across the filters. And that's from 400 to 900 nanometers. We have the LISA imaging IR imaging spectrometer, which is about 1 to 4 microns, and that creates an image cube. Builds up in the same way with a scanning mirror. We have TESS, which is a thermal IR spectrometer. I'll talk about TTCam in a minute. And then we have LORI, which is our high-resolution panchromatic black and white camera. I wanted to mention this T2 cam in particular. That is our terminal tracking camera. So this is part of the automated tracking that we have on Lucy. What we plan to do is at a certain point in near approach, within the last day and hours of approach, the spacecraft's pointing will basically, its knowledge of where the target is will be taken over autonomously. So the terminal tracking camera will basically be able to tell what the distance is to the target and the location. And based on the distance, the spacecraft will fire off different commands for different observations that we want to take at certain distances from the target. So we are highly dependent on the success of this autonomous system. And that's why we want to do rehearsals with the main belt asteroids before we get to our prime targets. And the science that we will be planning on doing there will be a combination of surface geology with the pan camera. We have surface color with the MVIC version of Ralph, and composition with the LISA version of Ralph. That's the spectroscopic data cube. We will get surface temperatures and properties with the TESS instrument, the thermal emission mapping spectrometer. So this will examine the physical properties of the surface, and just like sand on a beach heats up and cools off differently than the concrete sidewalk due to the properties of the surface, as we look at the temperatures on the sunrise versus sunset versus noon part of the asteroid, we can tell things about the surface properties and the makeup, the small scale makeup, how sandy or rubbly or monolithic it might be. We can also look on the night side too, of course, and see the cooling off on that side as well. Now these are flybys. We're not orbiting around. So as we come in, we will see kind of a crescent, and as we fly away, we will see the other half. We fly by on the sun side, so we will not see the farthest dark side. But depending on how fast the rotation of the object is, we will get some data, but this flyby is very fast. It is over, really, the meat, the central part of the flyby is over within hours. But, you know, the really good data of interest is still days. We will also be able to learn just by these things, infer things about the interior, how solid it is. Oh, one thing I didn't mention was the radio system on the spacecraft will be used to look at the Doppler shift as we fly by these objects to try to get an estimate of the mass by the deviation of the radio signal. So if we have an estimate of the mass from the radio, and we have an estimate of the shape from these visible observations, we have to infer perhaps what the unlit portion is like. If it's rotating fast enough, we can see all the parts that get daylight, but depending on the orientation of the pole, some parts we may never see. But we can infer a volume, we can get an estimate of the mass, so we can get a density. That tells us whether it's more a rubble pile or more monolithic, more solid, or some combination. And also we will look for other satellites and rings around these objects. So Lucy will be the farthest operated spacecraft on solar arrays. And this shows how the solar rays unfurl. You can see they're mounted on this cloth material. And these are 7.3 meters across, 2 of them, they're huge. At 5 AU, so out at the area of Jupiter, the 2 arrays together, all strings and circuits, will generate about 500 watts of power, so less than your microwave. At 1 AU, if we just have a single string, there's long strings and there's short strings, a single string, we still will generate 1,000 watts with just the long strings powered. If we had both arrays fully running at the distance of the Earth, it would generate about 16,000 watts. And just a beautiful picture of the launch. It really was a beautiful launch. Again, working on missions, the building is interesting and all the details and getting engineers to work with scientists, to work with managers, it's very interesting. Just the whole development on a schedule, under budget, is very exciting. And then getting the science down, of course, is amazing. But you get to see a launch too. And this was a beautiful launch in the morning, and you can see it, reflected in the water below, but going through this deck of clouds and over. And I just have to show this movie because it really was the most beautiful launch I've seen. And I was there with a lot of people who've seen a lot of launches, and they all agreed it was incredibly beautiful launch. Usually when there's a cloud deck, the launch it goes into the clouds. That was nice. And that's the last, at least, we will see of Lucy. So if you want to follow Lucy for the next 10 years, I recommend this website, which was created by Raphael Marshall, who also was the person who found Dinkinesh, that first orbit we were going to fly by. Dinkinesh is incredibly small. It's going to be the smallest asteroid flown past. And so we call it Dinky for short, for very small. But this is whereislucy.space. You can watch it live. You can update it for any date. Yes, I did pick today. So this is where the white dot is where Lucy is right now. And this little gray one there, must be Dinkinesh. So that way you can keep track. And other than that, that's just the kind of the highlight and the summary. So to make tribute to one last reference to Lucy from the old 1950s TV show that was very popular in America many decades ago. It was called I Love Lucy. So, of course, I have to finish every talk with the logo from the TV show I Love Lucy. And with that, I'd like to thank you very much.